Okay, sorry for late start. So, do we have any question from this time? If we don't have any question, let's start a totally new topic. So last time we talked about entanglement, and well, entanglement is the result of we having a composite quantum system. And I guess you are, you will look a bit different for now, but you will see later that this is also for composite system. But we're going to talk about this density operator. And so the chapter is about density operator, reduced density matrix, and purification. Okay, so what is density operator? Well, it's a different way to describe. I guess it's a more general way to describe quantum state. And the start point of thinking about density operator is that we might want to describe some classical probability mixture of quantum states. Okay, and or sometimes you can use this to describe quantum states which is not completely known. Okay, so for example, in our teleportation example, we have that Alice will do something, and so Alice got 4 measurement results, and Bob will get 4 corresponding states, and we say it's this spooky action at a distance. So Bob will get one of those 4 states, and before Alice passes the measurement result to Bob, Bob doesn't know which one of the state it is. And Bob knows it's one of those 4 states, with each one with 1 full probability. And if Alice just never sent her information to Bob, then we would like to describe what kind of quantum information Bob can extract out from this state. Okay, so this is a bit of motivation of density matrix. So sometimes we will get some classical probability mixture of quantum state, and we want to have a good mathematical formulation of this. Obviously, you can just have those 4 states and label them with the probability, but we'll see very soon that there is a much more elegant way to do this. That is, you are going to write into a matrix. And before we go to the matrix, it's important to note that this is something we need to do. So this density matrix usually most of the time it's not something you can describe by just having it depends on how you do this, but on face value you cannot describe it as just a quantum state, because the quantum superposition is different from this classical probability. Okay? So you say you have 1 full probability of each one, doesn't mean that the state is you add them all together into one state with equal weight. Okay? So quantum superposition and classical probability mixture is a different thing. Okay? And then let's see how we do the density matrix. I guess let's do this in slower way. Maybe a bit spoiler. So the end result is that the density matrix you get. So if you have a whole bunch of probability and a whole bunch of state, so you say you have a whole bunch of state that will happen with some probability, then the density matrix you get is this matrix. So you have the sum probability. So you basically average over this probability here, and the projector onto each state. So this is psi I cat, psi bra. This is a projector onto the state. Right, the cat is this vector, and bra is this vector, and you multiply it together, then it becomes a matrix. So each one of them is a matrix that's projected onto psi, and your density matrix is just this thing. Okay? And let's go back to the derivation a little bit. So the derivation is, we want something that can let us calculate this, a bit physical motivation. So we want to calculate this explanation value of A correctly. Okay? And so we want to say what's the explanation value of A if you have a whole bunch of psi, each happening with probability pi. Well, then we know expectation of A with psi is this nice formula. So you sandwich A with psi, and each one happen with pi, so you just average with pi, so you multiply pi and sum over I. Okay, and then here we do something. Okay, and here we do something nice. So yeah, and so we do something, I guess, smart. So first, this is just a number. So summation of each term is, well, this is just a number because we said it's a break it together, it's just a number. And multiplying pi is a number times number is a number. And the number equal to will trace of itself because we can see a number as a 1 by 1 matrix. So we can just write down trace here for free. Then we can use the cyclic property of trace. Okay, so we look at those three things. Okay, and the pi is just a number, so we don't care about it. So we look at the matrix part. So ABC together. So we think the psi part is A, and this A psi part is B, and by the cyclic property, we can move this A psi part to the front of our trace. Okay, so this is trace A and psi pi psi. Okay, and then we see that we see that the A doesn't depend on psi, and trace is linear, so we can move the summation inside the trace. So first we can move summation inside trace, and also then we can also move summation to this just summation on the I part because A doesn't depend on A. So we see that this is trace A, and this is summation I part. I guess I should move this down a little bit because we are blocking the I here. Okay, so summation I, pi, and psi. Okay, we are missing a bit of things here. Okay, so yeah, and so this is a derivation. We see that kind of a bit of a motivating derivation. Oh, sorry, I forgot to have this. Let's see. This thing and this thing. Okay. Okay, so I should have this here and the summation I here. And anyway, this is a motivating derivation. We see that the end result is a trace between A and a matrix here. Okay, so this is a matrix that depends on psi and pi. So we can write down this expectation of expectation of A with respect to this size with probability pi into this very succinct form where you have all the pi and the psi in one term. It's just this summation I pi and the projector onto I. Okay, and yeah, so we define this thing as density matrix, and we just derive the first property of a density matrix. Is that if you want to calculate the expectation value of some observable, it's a trace of your observable times multiplying your density matrix. Okay, and yeah, so this thing is called density matrix or density operator, and density operator or density matrix because both of them it's a matrix, so it's called density matrix, and it's also called a density operator because you can think of matrix as an operator. Okay, but most of the time you don't really use it as an operator, so I like the density matrix name a bit better. Okay, and anyway, this is the definition of a density matrix, and also here we have a bit of physics name. So we call this it back. Nice. Okay, and yeah. Okay, so here is a definition of density matrix, and but we derive this just from we want this object, this density matrix, to tell us what's the expectation value of any observable. So it does tell us the expectation value of every observable, but we want this to actually describe all the quantum physics of this example. Then we need to check other things. Okay, so you want this thing to totally describe the system of pi and psi. This is a set of pi psi, and then we need to check two things. We need to check it can evolve and evolve according to some quantum rule, and it also tell us all the measurement result of this ensemble. Okay, and I guess before we do the checking, let's give a bit of handwriting example. Okay. And this is, I guess, this is a bit spoiler. So this example tells you that the density matrix is a bit weird because you have a two ensemble that looks very different, but they will give you the same density matrix. So, but actually those two ensemble we kind of see them already a whole bunch of times. Those are the measurement result we see quite a few times. So first ensemble is an ensemble between this 0 ket and 1 ket, so the eigenstates of the Z operator, and each with 1/2 probability and 1/2 probability. And so you do density matrix calculation, so 1/2 multiplying this projector actually equal to this 1, 0, 0, 0, and 1/2 multiplying with this projector equal to 0, 0, 0, 1. And if you add them together, you see this identity matrix. This is 1, 0, 0, 1 times 1/2. Okay, so this is the density matrix for this ensemble. Now we have an ensemble that looks totally different. There are ensemble of x eigenstate. So ensemble of 1/2 probability being the plus state, and 1/2 probability being the minus state. Okay. And from what we told in previous chapter, we know plus minus state are very different from 0, 1 state. But nevertheless, you calculate the density matrix. Now you do density matrix on this thing, so you have 1/2 projector onto plus, and the projector onto plus is another 1/2 times this 1, 1, 1, 1 matrix. And then you have 1/2 times the projector onto minus. Projector onto minus is 1/2 times this 1 minus 1 minus 1 matrix. And then you do the calculation, you see this off diagonal 1 and minus 1 cancel out. And actually the end result is 1/2, 1, 0, 0, 1. Okay. So so here is an example of doing calculation for density matrix, and you already see we have some weird effects. So you see two ensemble looks very different will give you the same density matrix. But still, we are going to say that this density matrix tells everything that you can learn from those two ensembles. And in fact, this will tell us that if you are given just one of those two things, one of these, you are given either this example or this example, you cannot really tell them apart. Yep. And so let's check that. So let's go back to check the basic property of density matrix. We are going to check the density matrix can describe evolution and measurement. Okay. And evolution. Okay, so we need to have a rule for evolving density matrix, and the rule is here. So we say in our postulate of quantum mechanics, we say our quantum state is always evolved with some unitary u. Okay, and so if you are evolving the state with unitary u, the density matrix is evolved to this density matrix. So you sandwich your row with a u and a u dagger. Okay. And so I guess the proof of this work is just we derive this what will happen to the corresponding matrix of evolved ensemble. So we have so the logic is here. So at the beginning we have an ensemble of probability pi with a state psi, and then after you do this evolution, every psi becomes state u psi I. And so you have an ensemble with a probability pi with a state u psi I. Okay? And then you just calculate the evolved density matrix. Okay? So you start with starting density matrix is the sun I pi and psi projector, and you evolve it and it become pi, and some PI and projector onto this U psi I. So it's U psi I times the dagger of U psi I. So it's a psi I U dagger. Okay. And then here, once again, we use linearity of matrix multiplication. So you see this U doesn't depend on I, so you can pull this PI and summation I inside. So you have U, you have U times this just a row and U dagger. Okay, and yeah. So here, I guess the proof is. What we prove is that you can write the evolution of your density matrix in a very succinct form. Okay, so you have a starting density matrix, and with some example, then the example evolved, you have a corresponding density matrix. But the evolved density matrix can be described by just your starting density matrix and the U. So you see this expression don't involve any PI and psi. You can just describe this thing with U and the rho. Okay, so that's an important part. So the evolved density matrix only depends on P and the U. Okay, so that's write it here. Only depend on U and the rho. Okay, so you can describe the evolved density matrix. Okay, then the next thing we check is measurement. Okay. So now this is quite a complicated check we need to do. Okay, so let's see. So because well, there are many probability. So let's do it in most general form. So we're starting with some measurement we want to do. So generalized measurement with set of measurement operator is big M sub small m. And then we have an example of pure state, this set of PI psi I. Okay. Okay, and let's do this one by one. So if we have a state psi I, and we want to see what's the probability of, so if a condition will stay with our state psi I, and then we want to see what's the probability we get outcome m. So we want to see the probability of getting each outcome. And this we know how to do. This is just well, the measurement that we talked a lot about in previous chapter. So it's this mi size absolute value square, and its absolute value square you can write it in this inner product form. So it's this psi mi m dagger big M dagger small m and big M small m and psi. And then once again we use our trace cyclic trick. So we know this is a number, so we can add a trace, and then we cyclically move this psi to the end. Okay. And we use this trick, and then we can get the psi part together and all the m part together. So this m dagger m part together. Okay, and then we can calculate the. Okay, so this is the probability of getting m if the state is I. Okay, now we can go calculate use the probability rule to get the probability of getting m when you have this whole ensemble PI psi. Okay, and so the probability will be conditional probability times this individual probability and something together. So probability you get PI, then once you get PI, the probability you get VM, and you sum over OI, and yeah, so it's a sum PI, and then this term is this term here. Okay. And once again, we use the linear rule, so we put this PI inside this trace and put this summation inside this trace, and yeah, only thing dependent on I is this PI and psi psi. So once again, it becomes rho. Okay. So it's just a rho here, doesn't depend on PI and psi. Okay. So we see you can describe the probability of getting some outcome as just a trace m dagger m and rho. Okay. Okay, and but there are other things we want to check on this measurement. So here we check the probability, and we want to check the post measurement state. Okay, so after we get some result, result m, we will get some post measurement state where it was some psi I and will become some psi m. And it's some density matrix, and we should have some post measurement density matrix too. Okay, and so first we have this psi m, Excuse me. So psi n is the normalized post-measurement state. It is nm psi, and they normalized by dividing its norm. Excuse me. Okay, and after so after we get the result m, we will get an ensemble of state with different probability distribution and different post-measurement state. Okay. And here the probability gets tricky because now we need to calculate this conditional probability. It's a bit of calculation. Okay. And anyway, our density matrix will be according to this rule. Okay. So you have an ensemble with different probability distribution and different states. And the corresponding density operator should be, once again, summing over those probability times the projection onto this state. And we already calculated the post-measurement state, so we write it here. It's this m psi psi m dagger and this normalization here. Okay. And as we say, it's hard to calculate this probability, and we need to do this slowly. Okay. So yeah, here we have probability calculation. So probability A condition on B actually equal to probability A times probability B condition on A divided by probability B. And this is by base rule because, okay, so here we have a bit of derivation. So probability P condition on B, so it's kind of like the calculation we do here. Well, I guess it's a bit different. So let's do this. So probability of A, event A and event B both happen is equal to probability of event B happen, then condition on event B happen, event A happen. And it's also equal to probability of event A happen, then condition on event A happen, event B happen. So if this thing equal to this thing and then move things around, then we see this P A condition on B equal to this part divided by PB. Okay. And so here we have two events. One event is getting measurement outcome being M, and another event is you draw from your starting state and being I. Okay. And so this is a bit confusing, but we just need to walk through the calculation. So now we have a PI condition on M. We just put things inside. Is a PI condition on M equal to PI times PM condition on I and divide by PM. Yeah. And then this thing here, so we have a whole bunch of things, and then the state part we have this M psi and psi M dagger, and divide by this term. But this term we already it looks very familiar, and it's this PM condition on I we already calculated before. Okay. This is when you have state I and you get probability of getting outcome M, because it is nm on psi and absolute value squared. Okay. So this is also Pn condition on I, and they will cancel with this Pn condition on I. So in the end, we can get something nicer. Okay. So we have Pi here. Well, Pi is just Pi. We were writing it P sub I is the probability of you get I in your getting state psi in your ensemble, and PM we also calculated before. Okay. And PM we calculated here, and it is a trace and dagger and row. Okay, and it's here, and so it's this thing. So the result is that, okay, so once again, at this step we can do what we like to do. So once again we use the linearity of this matrix multiplication and look through all things that depend on I, only Pi and this projection on psi. So once again we see that this can be written as an expression with rho. So it is n rho n dagger and divided by trace actually this is equal to. Okay. And I guess a better way I want to like to write this is you can write this as a trace of use the cyclic property again. So this lower part equal to this thing, trace n rho and dagger. Okay. And why do I like this? Because just like in the pure state case, you can remember this very complicated formula by just knowing that this is the post-measurement state is basically this M row and dagger, and they just normalize by its trace. Because very soon we'll see that every density matrix has a trace equal to 1. Okay, and yeah, so and you can kind of feel that to do density matrix calculation, you always do this sandwiching with operator thing. So you see that when you do evolution, you have a U row U dagger, and when you do measurement is actually very similar to evolution. When you do measurement, it becomes M row and dagger, and the difference between measurement and evolution is that you have this post-measurement state. It's usually subnormalized, and you need to normalize with its norm. Okay, and in terms of density matrix, the norm is a trace, and so we divide by its trace. Okay, any questions so far? So this is the derivation. So we see that when we do time evolution and measurement, then we can still describe the resulting ensemble and measurement statistic, etc., all with the density matrix. Okay. So yeah, you can describe the measurement with density matrix, and then you can describe evolution with density matrix. Okay. Here. Okay. And yeah, okay, and yeah, let's give a bit of notation. So we talk about pure state. So what's a pure state? Pure state is a term that that's opposite to mixed state. Okay, and so what's a pure state? Pure state is what the kind of quantum state we were describing. So the quantum state that can be described as just a Kt vector. Okay. If your state can be written as a Kt vector, it's a pure state. And for pure state, you can think it's just this state with probability 1. And so any pure state, you can also write this density operator, and it's rho and equal to this projector onto your state side. And I guess here, people, so a bit of critique of what do we do. So you look at literature. I guess this is also what you will do yourself. Okay. Sometimes we will also do in this class is that we will call either this thing or this thing as pure state. Okay. Both this rho and the K side, people will call it pure state, and they just need to be careful about context. So you need to distinguish whether we are talking about pure state as just a vector, or pure state as the density matrix that correspond to this vector. Okay, so yeah, a bit of ambiguous notation. Both the matrix or the vector is called pure state. Okay, and so that's pure state. And now we have mixed state. So mixed state is a probability mixture of pure state, and so it's a density matrix that just another pure state. Okay. So if you write your probability mixture as a density matrix and find out that it cannot be written as just a one-dimensional projector, then you are in a mixed state. Okay. And here we have a homework that asks you to check this property that lets you check whether your density matrix is a pure state or not. Okay, so you can check the trace over your rho squared. So if your trace over your rho squared equal to 1, then your state will be a pure state. And if it's less than 1, then it's a mixed state. Okay. And yeah. Okay, basically you just check their eigenvalue. So a bit of a hint for homework. Okay, so this is a pure state and mixed state. Okay, and and okay, and here we state something even better about mixed state. Okay, so we have defined our density matrix as a probability mixture of pure states. Alright, so we have our ensembles here. We write this pi and psi. So it's a probability mixture or pure state. And then you might ask, what if you have a probability mixture of a mixed state? Okay. Sorry, a bit too much. Okay. So what if we have an ensemble mixed state? Then do we need an even more complicated expression to describe them? And fortunately, we don't need to do that. So if you have an ensemble mixed state, it's just still a mixed state. So you can just do it with another density matrix. Okay. And so here is a bit of a derivation. So if you have a whole bunch of density matrix, so you have each whole bunch of rho I with some probability pi. Okay. Yeah. I guess here, yeah. So you have this ensemble of, I guess I should write it here. So if you have an ensemble of pi and rho I, okay. And so each rho I, okay, and then each rho I, well, is a mixed state, so it corresponds to some ensemble of pure state, so some Pij and Psij. Then we can write the total density matrix by just this base rho as a probability mixture of those Psij's. Okay, so it will be summation over ij and with those Psij projectors, and each one has a probability. So first you need to be inside this density matrix I, and then multiplying with this conditional probability Pij. So the Pi times Pij anyway is another probability, and yeah. So I think here is you sum over. Yeah. Here you excuse me, and then here you do. So the total density matrix is this thing. Then you can sum over J, and then you see that sum over J, Pij, Psij, and it's just a definition of a rho I. Okay, so we can sum the Pij, Psij together, and it becomes rho I. So you see that the rho can be calculated from this ensemble of Pi and rho I, and it's just it's just a weighted average of those rho I. It's just a sum Pi rho I. Okay. So not only we prove that it's another density matrix, because once again it's a probability mixture of a pure state, and actually there is a very simple formula to calculate it. You have a probability mixture over density matrix, then you just average over those density matrix with the corresponding probability. Okay, so yeah, so rho is a mixture of the mixed state rho I with probability Pi. Mixture or mixed state. Okay. And okay, and here we have result of using the density matrix to describe something in quantum measurement. Okay, so suppose we have suppose we have a quantum state, and so if we do we have a quantum state, and I guess we start with we started with a modular case. So we start our quantum state with some state rho, and then we do a measurement with I guess I should so we start our state with rho, and we have a measurement. This measurement say big M. Okay, and we do this measurement, and as we derived before, we can get some measurement outcome M, and then our density matrix will become the corresponding post-measure state, post-measure density matrix. So it's this thing here. Okay? But we can describe something more here. We can describe a bit of a weird situation where we do a measurement, but we doesn't know the result. We kind of forgot the result. Okay. So we do a measurement and we forgot result, then we'll get another density matrix. Now we can describe this. Okay, and so what we get is we'll get the probability ensemble over probability mixture over the post-measurement density matrix. Okay, so we have this summation m and probability of you measure rho and on this you measure this mm on this state rho and get outcome small n, so this is pm and times the post-measurement matrix rho m. Okay, so you write this out. So pm we calculated both of these before. So pm is the trace m dagger m rho, and rho m is m rho m dagger, then trace m dagger m rho. And we see those cancel out, and we actually get an even simpler result. We get this is this post-measurement state density matrix, even though we don't know the measurement result. Is still something different, so it becomes the sum over m and n sub m rho and m dagger m. And one thing to note here is that this thing, even though you do measurement and you don't know the measurement result, but just the effect of doing measurement can change your state. And so in general, this thing is not equal to your starting state rho. Yep. And I guess a bit of motivation of why we want to do this is something we do is when in a teleportation setting, Alice will do a measurement here, and this will change the density matrix of the whole state, even if Alice doesn't recall the outcome. Okay, so if you don't recall the outcome, Alice and Bob, those 3 qubits, have some density matrix. But if you know the outcome, then we'll pick a particular m, and your state will become this thing. Okay, and I guess let's see some example. So, and here is an example. So, measurement that we do a lot of times. So you measure the plus state in the computational basis 0 and 1. Okay. Okay, and the starting density matrix rho is this density matrix corresponding to plus state, so it's projected onto plus. Is this 1 over 2, 1, 1, 1, 1. Okay, and after you do measurement, then we have to do this whole bunch of time, and we know the result is that you have a 1 over 2 probability getting 0 and a 1 over 2 probability getting 1. Okay. So it should be 1 over 2 and projected onto 0. Plus 1 over 2 projected onto 1. And here also you just use the density matrix calculation to see that they still fit what we think. Okay, so after measurement, what you get is the summation m and m rho m dagger. And so the measurement operator here, so measurement operator for measuring in computational basis, just a projector onto the computational basis. So you have m0 being this projector onto 0 and m1 being this projector onto 1. Okay. And then you can do matrix calculation here. And so you have this whole string of matrix multiplication. But then in the middle part, you see you have bracket here. So this is just become number, this become number, this become number, this become number. And you calculate the inner product, you see that this is 1 over 2 here, and this is 1 over 2 here. And then the remaining part, you just have this 0 cat, 0 bra, 1 cat, 1 bra. So that's 0 cat, bra, 0 projector, and this is 1 projector here. Okay, so we go to different way to do our calculation. We see the calculation result fit, and what we get is we get this 1 over 2 times the identity density matrix. Okay. And this kind of density matrix where you have identity multiplied by some constant is called totally mixed state or maximally mixed state, because you can kind of feel it's maximally mixed because in every direction it has the same probability weight. So you see the same probability weighting between the 0, 1 direction, and from our, let's see, from our example a little before, you see that it's also the equal probability mixture between plus and minus. So it's really nice. Okay, so that's a totally mixed state. Okay. And here we write down some homework you can do, so you can try to calculate the post-measurement state of total of teleportation. So what is the state of the system after you do the measurement here? I guess there are several different things you can do, but the homework will probably ask you to see what's the post-measurement state of the state B has after A do the measurement, and doesn't tell B the measuring result. I guess that's technically a little bit different from what we do here, because here we don't reduce the dimension, but it will be but this calculation will be a bit related to what we are going to talk about on the later part of this chapter. Okay, but anyway, when we know that when we do measurement here on A part, then there is a corresponding ensemble on B part, and they can calculate what's the density matrix corresponding to the ensemble of the state on the B part. So what's the density matrix on this fourth state? Okay. And I guess a bit of spoiler, we talk about totally mixed state here, and you are going to check that the ensemble is going to be totally mixed state no matter what the A's input, A's unknown input is. Okay, and we have 4 minutes. I think it's a bit tricky to finish here, so let's state a theorem here and maybe have our break a bit early. Okay, and so far we have characterized a density matrix or density operator as a probability ensemble. So basically we define them as associated to some probability mixture of pure states and or even probability mixture of density matrices. Okay, but actually there is even freer, even more I guess more fundamental way to define this is you don't really need to always find the ensemble to have a density matrix. We can have a density matrix just for our we can say a matrix is a density matrix if it just if it satisfies those two rules. Okay? So density matrix need to be trace 1 and they need to be PSD. Okay? And trace 1 basically means that so you look at its eigenvalues. So from PSD is unitary diagonalizable, and it tells us all its eigenvalues are greater or equal to 0. And then from the trace 1 we have the eigenvalue is some equal to 1. And so those eigenvalues will basically be probabilities for your density matrix. So they should be greater or equal to 0 and greater or equal to 0, and they should some equal to 1. Okay. And so this theorem tells us that as long as your matrix satisfies this rule, then you can find the ensemble correspond to your density matrix. So this is a physical thing. And from our derivation before, we know that this density matrix will tell us everything about your ensemble. Okay. And then also the other way around, so there is a two-way want to prove this. So first is that you have an ensemble and you write a density matrix, and then you will satisfy those two rules. And the other way is if you satisfy those two rules, you can always find the ensemble. Okay. And so that means that you only need to check your density matrix as these two things and know that it's valid. Okay. And so I guess here let's have an earlier stop and take a 10-minute break for now. And then we'll continue with the proof of this. 这次的作业做 density matrix 吧。我们需要教到哪里？应该 teleportation 最后一题是什么？有 reduce density matrix 的吗？最后一题这个嘛 ，unitary U。
我其实也不知道这题。
哦，这是一个有趣的问题，这个有点偏 integral 的部分呢。
对。
没有 state。
上次删掉好多 integral 的问题。
哦，那可以把我们加一些回来，看你想加。为什么第一题是第一题 density matrix？ 对。4题的话，加不加都可以吧？看你。你决定一下。
对。再把上礼拜原本删掉的都加回来。
我们30几题啊？不用多出就是，先够看一下有没有什么比较重要的或者比较有趣的。好像也没有太多。我记得2出过了。
这个3个，这个跟这个。
4蛮讨厌的，3出一下好的。3其实好像蛮快，就是虽然人家不要被 C 之后说那么，就是。
那1也删了吧？1跟3都删。
对吧？1不知道要不要。就那个1跟3好像都比较重要，1可以少几题吧，1把少几题加回来，然后3让它算一下，3应该要有就是，如果不行的话就把这个礼拜的多拿一点掉，可能就拿一点掉再丢到后面这样。你看一下。
确认一下。
可以压缩一下。
应该蛮确定1是1、2、3。对，所以就。
那就把1的选1、2个让他们算，然后3让他们证明，然后看一下这个礼拜的话有什么可以先拿掉的吗？第一题我还蛮喜欢的，还是真的不行就把4拿掉好，4也没有一定要整，只是4是个4是个不错的考题，还是3。3刚刚讲了，好不好？3其实有点无聊。
好像拿掉3，然后加。
看一下这边要拿掉这个，可能可能3可以拿到下一次吧之类的，对啊。
3拿掉，然后加
上一次的1、3之类的 ，OK。
这个等级是怎么称的？就是为什么可以直接这样 trace？他们听懂。
因为它是一个数字，就是每个数字都等于自己的 trace 嘛。因为一个数字可以当做一个1乘1的矩阵，然后。所以1乘1的矩阵 trace 就是那个数字自己而已。
所以它可以直接写是这样。
对。对。
期中考有确定是办在第8周的礼拜4吗？然后
应该是。
好，那发考卷会确定什么时候发吗？还是
发
说反正我
考卷要看我们改完嘛，就是不太确定，1-2个礼拜之后吧。
还是说反正如果不小心没领到，就去实验室？
对啊，可以去实验室啊，对。看起来可以吧？看要不要把这个砍的烧机器吧？看
这个算超快的吧？
哦，是吗？
这只不过就
那有点快啊，这也是可以。那差不多吧。再看你配分要不要调一下。总觉得第5题好像比前面的难很多。
那上次也是10分。
对啊。
其实我觉得
你可以调一下配分。
这次的都还好。
哦，对。
因为这都是计算。
我可能会把4跟5都变20吧，4感觉比较简单。4就硬算一下就好了。
原因是因为这边要算6个，这边要有6个东西。
哦，好。
你要互相，所以是。
那就这样。
所以每个5分。
好，那就，其实不是算6个。哦，好像是啊。
就是互相都要全部测完，所以1个5分。是数量问题。
想真要测到6个吗？哦，好像是要。OK， 那就这样。OK，
其实这要算最久，应该是第1题，我觉得是。
第1题都要算。OK， 那就这样，那我们开始上课。Okay, and yeah, let's come back to density matrix, and let's start proving this. And as I said, we are going to prove 2 things are if only if. So if we have an ensemble, then the corresponding density matrix satisfies those 2 things. And if we have a density matrix satisfy those 2 conditions, we can find an ensemble. Okay. And the only if the relation is easier, so if from an ensemble get a density matrix, then we only need to do calculation directly. Okay, so we check both conditions. First, we check the trace. So trace row equal to, trace row equal to trace of okay, and the row is pi and some IPI and psi psi, and here we already do 1 step, so we use the linearity and move the trace inside because because pi is a number, so I can pull all of the trace, so only a matrix part is this thing. And then we use the cyclic rule of a trace, and so this is just psi inner product with psi, but each psi is a normalized state. So this inner part just 1, so we have summation IPI and equal to 1. And then also need to check this is positive semi-definite. means that you sandwich your row with any other state size, it should be greater or equal to 0. And yeah, so let's keep doing this calculation. So it's some IPI. And once again, by linearity, you can have the sandwiching on just your matrix part. So this psi and psi, then psi. And it's but this thing, the psi inner product and the psi inner product is a complex conjugation to each other. So it's just the psi and the psi inner product and opposite value squared. And so the end result is you are averaging over a whole bunch of things that are greater or equal to 0 because opposite value squared. And so this thing is greater or equal to 0 for every psi you pick. Okay, so this is the easier direction. And the if direction, then we need to do a bit more thing. But basically what we do is we do this eigenvector decomposition for our row. And you need to start from your state is positive semi-definite. Okay? And yeah, I guess the proof here, yeah, the proof here is, now I look at it, it's a bit circular. But anyway, you can prove that if matrix is PSD, then it's unitarily diagonalizable with eigenvalue lambda j being positive. Okay, and yeah, so this will basically become our ensemble. Okay, so we use lambda I as our pi, and this lambda j as our pj, and those eigenvector j. Those eigenvectors j will be our vectors. Okay. So we know j are also normal because of the spatial because this row being normal, and those lambda j will be greater or equal to 0. So from just this PSD. Okay. And we want these lambda j's to be probability, so they need to be greater or equal to 0, and they need to sum to 1. Okay. And yeah, but when you calculate the trace of this thing, you see that the trace is just a sum over those eigenvalue. So trace equal to 1 just means the sum over this eigenvalue 1. So you can just view those as probabilities, and our ensemble lambda j and j is an ensemble that will give the density matrix row. Okay, so that's a proof. You can get a density matrix. So you can get an ensemble from your density matrix. You just need to diagonalize your density matrix. Okay. Okay. And yeah. So now we have this characterization of density matrix. Now we can rewrite our quantum mechanics postulate with the density matrix. So we can just describe everything with density matrix row. We can forget about the ensemble interpretation. Now we just have a density matrix. That's a PSD matrix with a trace equal to 1. Okay, and yeah, so we have a postulate. So we have our state associated with this Hilbert space H. And then we describe the state of a system as the density operator. So density operator or density matrix is a matrix, and everything is an operator. Is an operator that makes from your space to back to your space. And anyway, it's going to be a PSD matrix with a trace 1. Okay. And they also satisfy this ensemble interpretation. So if you have a probability mixture over systems of different density matrix, then resulting density matrix is some I, pi, rho I. Yeah, so this is kind of what we get for this density from this density matrix formulation is that you can write the classical probability mixture. But in return, you need to write many more things. You are now writing matrices instead of vectors. Okay. And then we have this evolution rule. So the evolution of your system is described by those unitary transformation. and is described by this unitary operator U, and the resulting density matrix rho prime will be U rho U dagger. And we have measurements. So measurements, well, the measurements themselves are still the same. They are described by this collection or measurement operator M sub M, and they need to satisfy this completeness relation. Thus, summation I M dagger M be equal to identity. So when you measure your density matrix with the set of measurement operator M, then the probability of outcome M is the trace of n rho and dagger, or because cyclic is trace of n dagger and rho. Okay, and the post measurement state will be this n rho and dagger and normalized, so dividing by its trace. Okay, and but now we have two different ways to describe the post measurement state. So if you know your measurement outcome is M, then you have this probability and this post-measurement state. But we see that because now we can describe probability mixture, we can also say what if you just do measurement and doesn't know the outcome, then the corresponding density matrix will be this interesting state. So the summation M, M rho and dagger. Okay, so it's actually a simpler form than this thing. It's this upper thing and summing over all the possible outcome. Okay, and then finally we have the tensor product, and this is just basically same as before. So you have multiple systems, then the corresponding Hilbert space is the tensor product of the Hilbert space. And then if you prepare, I guess the only different part is you have prepared your system each in the state rho I, then the joint state of the total system is this rho 1 tensor rho 2 all the way to tensor rho 1. Okay. So kind of like just before, but instead of tensoring between vectors, now we have tensoring between over matrices. Okay. So it will give a huge matrix. Okay. So this is postulates of quantum mechanics with density matrices, and yeah, obviously the unitary evolution and the measurement, you also need to make it into larger space if you do unitary and the measurement on the specific subsystem. Okay, and then now we want to talk about something that's mathematically very complicated, but I guess conceptually it's nice to know this happened, but actually we don't use it so much, so I guess I will skip through the mathematical detail of this. Okay. And anyway, so what we are talking about is the equivalent of different ensembles, and we kind of already spelled this a little bit just from the starting of today. So we say that there are different ensembles that will give you the same density matrix. Okay. Yeah, so this is quite interesting. In fact, we see that where the do this calculation, we see that this ensemble of 1/2 being 0 and 1/2 being 1, and the second ensemble of 1/2 being plus, 1/2 being minus, actually have the same density matrix. Right? So if you are given this ensemble and this ensemble from the postulates that we give you, we find out that we can actually tell which one it is. Okay. And yeah, so this might feel very weird to you, but you can do calculation, and you see calculation and check out. You do whatever measurement you want to do on those two things, they will give you the same measurement statistic outcome. So you really cannot tell which one it is if you are just given this thing or this thing. Okay. And now this theorem, okay, so I guess the most important part is already here, so you need to know the different example of state will give you the same density matrix. But now we have a bit of theorem tells you that when does this actually happen. I guess here I'm going to say some better word for this theorem. Okay, so it's a really cool theorem, but from my personal experience, you don't actually use this too much. Okay. So it's a nice theorem, it has a nice form, but I don't remember too much application on it. Maybe there is some relation to it if you really study more quantitative information. But yeah, it's nice to know. And also the proof is a bit annoying because there are very many edge cases. So yeah, we'll probably try to skip through the details. But anyway, so much for dissing this theorem. Okay, and now let's back to see what this theorem says. It says that if you have two ensembles, so Pi psi and Qi phi I, and so and want to then to generate the same density matrix, and we see that this happening if only if we have this very nice equation. So this equation looks very nice. So we want the psi tilde equal to excuse me. So psi tilde equal to some j uij phi j tilde. And okay, so now this equation looks a bit funny. It has three things that we never defined before. Okay, so what's the psi tilde? Psi tilde is basically psi normalized with the probability pi. Okay, so psi tilde is a way to combine is pi and psi, so it's a square root of pi times psi. Okay. And similarly, we have this normalized or subnormalized phi is a square root of qi times your phi. Okay, so you have psi tilde and phi tilde. And what's uij? Uij is just whatever thing you can find. So I guess here if you want to be mathematically precise, we need to say exists some ui exists u with uij. Okay. So mathematically, we should say exists u and so okay. So sorry, I am spelling exist wrong. Okay. Okay, exists u, and u is a matrix. Is a matrix, and the important thing is it's unitary. So there is a unitary matrix, and so if there is a unitary matrix U, with its element being those small uij, and it will link this psi from phi. So link from this psi tilde from this phi j tilde. Okay. So if there you can find some u to link from psi and phi from with this kind of relation, then these two ensembles are equivalent. They give you the same density matrix. Okay. And yeah. So it is a unitary matrix U, such that this equation is satisfied. Okay. And yeah. So let's say start talking about why this theorem is very annoying. This theorem is very annoying because if you just look at this, it's okay. You have some unitary transforming. But this is annoying because there are three numbers that are not the same here. Okay, so there are basically three dimensions. So first is the dimension of your Hilbert space. You have well, first those two things should be in a same Hilbert space. Otherwise, this will not work. Okay, so there is the dimension of your Hilbert space. And then you have dimension of a span of this vector or this vector. But you want them to give the same density matrix, so the span should be the same. Okay. So, but anyways, there is a dimension of the span, and then there is also the number of vector here and the number of vector here. And yeah, so all those four, so they are actually like four numbers. So all those four numbers are different, and that make the proof very annoying. So you need to pay the whole bunch of zero to make the dimension match, and so that you can actually have a unitary matrix here. And yeah, as I said, that's really annoying. The lecture note should have the full detail, and let's try to have this, try to prove, have the non-annoying part of the proof. Okay. But first, let's see some example of the proof. Okay, so we have our two examples. So one have 0, one have 1, and one have plus, one have minus. Okay, and then we have our. Okay, so we have our psi tilde and the phi tilde as square root of those 1/2 times our thing. Okay, so we have our I guess this is psi tilde here. Okay, psi tilde here, and equal to something times phi tilde, something times phi tilde. Okay, so this part is psi tilde, and this part is phi tilde. And then we have our u's here, so psi tilde 0 equal to 1 square root to phi tilde 0, 0, and 1 square root to phi tilde 0, 1, etc. Okay, and so anyway, so this is a 0, 0 component. This is and as we said, this is a 0, 1 component. So this thing. And this is a 1, 0 component, and this is a 1, 1 component. And so we have our u here, so u0, 0, u0, 1, and u1, 0, and u1, 1 here. And then we put them together into a matrix. We see that our u, I guess I should probably make a big u here. But anyway, so the u matrix here is this 1 square root 2. 1, 1 minus 1, and it's a Hedema matrix. I guess it's kind of not too surprising you have Hedema matrix here because it's the transformation between 0, 1 and plus minus. Anyway, but I guess I don't. Well, this is a bit of a different transformation from. So on one hand, it's not surprising you have Hedema here. And on the other hand, it's not very straightforward to see why you had Hedema here. But anyway, it's Hedema here. Okay. Yeah. So that's equivalence between these two examples. Okay. Then now let's go to our general theorem. Okay. General theorem. Once again we have if only if. So we want to see. If they generate the same thing, we'll get this relation, and if you get this relation, you can show they generate the same thing. And so I guess the easier direction is if direction. So if you satisfy this relation, yeah, so this is quite straightforward. So you can now write all your side as a linear combination of your phi. I guess technically you only need to write the psi tilde as a linear combination of phi tilde. But here you see very quickly that why we want to define those psi tilde and phi tilde, because you can use them to write down the density matrix really quickly. Okay? So you see that the density matrix related to psi is just a summation of this psi tilde ket and psi tilde bra, and similarly you have this phi tilde summing together equal to this rho phi. Okay? So yeah, this is why we want to define those tilde. And as we say, we can express psi tilde as phi tilde, and so let's write it out. And well, it's going to be quite complicated. So you have a summation right here. So I guess here let's do the math carefully, just for some to show you how to do math carefully. So you have this summation I, and each side. So this side can be broken into summation j phi tilde j. Okay. So you have another summation over j, and then uij, then phi j tilde. And then this psi tilde you need to also break it into summation of phi tilde. But then you need to have a different index here. So you already have summation j here. Then you need to have a summation k here. So you have a different index to summation. So summation j, and because everything is adjoint, then this broad psi tilde becomes this bra phi tilde, and then you have this UIK, and you also need to take complex conjugation here, because you have the adjoint of this equation. Okay, and I guess adjoint over this equation, you get a brought here, and summation is still summation, and those complex number get complex conjugate, and then this this kate become a bra. Okay, so you got this thing, and and then when we have UIK star, so you have summation I, UIK, UIJ and UIK star, UIJ and UIK star. And so what's this thing now? You think U as a matrix, and those are so UIJ are elements on the J0, and UIK will be elements on K0. And so this summation is J's column and the K's column. And so this summation will be inner product between two columns of U. But we know U is a unitary matrix, and I think we state, we should have stated this at the very beginning. For unitary matrix, any two columns are going to be also normal. So the inner product is 0 if J don't equal to K, and equal to 1 if J equal to K. And so this summation becomes delta JK, and then you do this summation of over delta function. You can just get rid of it. So we actually cancel J here. So the summation J with delta JK just means you need to make a J equal to K, J equal to K. So you are left with summation K, and then J become K here. And as we said, this is rho phi. Okay, so this is easy direction. Okay, and now let's try to do the hard direction. Okay, let's see if I can try to do this. That's skipping all the annoying space doesn't fit part. Okay, so the hard direction. So we have our psi tilde and phi tilde give us the same density matrix. Okay, and let's say the density matrix A. And the proof strategy here is quite straightforward. Quite straightforward. So with a density matrix, and what we would like to do is we diagonalize it. Okay. So we already said that because it's PSD, we can diagonalize it, and it has some. Okay, so now we have even more decomposition. So we have A with eigenvalues, so this is summation lambda k, and eigenvector is kk. And then we use our tilde notation again. So we have A as this summation k, and k tilde. And so here you already see a very annoying part here. Very annoying part is some lambda might be 0. Okay, and if lambda not equal to 0, then some of those k tilde doesn't exist. But let's pretend that doesn't happen, and that can be dealt with. You just need to be careful about lambda k equal to 0. And now let's see the idea of the proof. So the idea of proof is, so why we want to do this is we can connect psi and phi through this k, so, or psi tilde to phi tilde through k tilde. So what we are going to prove is that psi tilde, then you can do a unitary transformation to k tilde, and k tilde you can do another unitary transform to phi tilde. And so you know psi tilde is U1 times U2 to phi tilde. So but you know two unitary matrix multiplied together is also a unitary matrix. So psi tilde and phi tilde is connected by a unitary matrix. Okay, so that's the idea. And let's see. Okay. Psi tilde. Okay, and that's assuming we get rid of the, we ignore the, okay, let's see, psi. Any eigenvector of A. Yeah, oh, okay. So if we assume we don't have, okay, so here we spend a lot of time dealing with the lambda k equals 0 part. And, but as soon as it doesn't happen, then we can ignore all the middle part. And if we don't have a lambda k equals 0, then we have k tilde being, k tilde being all the eigenvectors normalized. But we know the k's are, we know k are eigenbases of the whole space, okay? Because yeah, that's just what happened. Because we do spatial decomposition and k is for orthogonal basis of the whole Hilbert space. Okay, so assuming lambda k equals 0 doesn't happen, then we every k give you k tilde. So k was also normal, and but so k tilde is still orthogonal to each other, and they are still a basis for the whole Hilbert space. And because k tilde is a basis for the whole Hilbert space, you can write your psi tilde as a linear combination of k tilde. Okay, so yeah, so here is the important thing. So we want to write the psi tilde as a linear combination of k tilde with some coefficient Cik. Okay, and yeah, then we just prove that this Cik is a unitary matrix. And let's see if I can do this. Let's see if I can do this easier. I guess you just need to do calculation. Okay, so we have that. Okay, so here we use our equation. So A equal to this sin I psi tilde, also equal to this sin k tilde. And okay, and then then as we say, we write this psi tilde as a linear combination of k tilde. So let's break this equation into whole bunch of summation. So this is sum over I. And because I'm not sure we want to do this, but okay. Oh, I guess yeah. So this is from this equation is from here. Okay, so let's try to go through this slowly. Okay, so this equation goes to this equation, and just like before, we need to break each of the psi tilde to different index. So we have this is original summation I, and the psi tilde break into summation k with k tilde, and then this psi tilde break into summation L of L tilde. And we already do change of ordering of summation, and so we have the coefficient with k and the coefficient with L, and sum over I, because this part is the only thing dependent on I. Okay. And then we just want to check that. Okay, I guess from here we are being very careful here, but let's just get an idea. So you compare this thing to this thing, and you know that k tilde are orthogonal vectors here. Okay, and so this thing you sum over I. This is some coefficient with so the middle part. So the what we are going to try to show is the middle part is we want this thing to be, so I is already summed over, so this is some function of k and L. So we want this thing to be delta KL. I guess our notation is delta delta KL. Okay. And I guess you want to go for mathematical is here. but basically the idea is that, well, the case are orthogonal vectors. So if you have the summation k kind of a diagonal in k, I cannot really say this as a matrix, but you feel that here you only have the diagonal element here, you only have k and the same k here, and now you have all the possible k and L tilde, but because the k's are orthogonal, so you want this thing to be equal to this thing, then the coefficient here should be same as the coefficient here, and the coefficient here should basically be delta KL. So you have 1 only when k equal to L, and that will correspond to the kk here. Okay, and yeah, so in this part you can actually prove that yeah, you can actually prove that this is true. Okay. So using using even more calculation. Okay. So in the end, you will calculate that using k tilde and L tilde being orthogonal vectors, you can prove that this thing here is actually delta KL. Okay, and finally we get this summation being delta KL. Then we just have the reversal of this argument. So now we think about the C matrix with the element being Cij, and then we see that all its columns are orthogonal. Then C is all its columns of C are also normal, and so this thing columns of C are also normal. So C is a unitary matrix. Okay. Yeah, but to say C is a unitary matrix, it will be even more annoying because, as we said, so this is another you need to pay the zero part, or I guess pay the extra columns to C, columns or rows to C, because the number of indices I and the number of indices k doesn't match here. Okay? So C might not actually be a square matrix. It's a matrix with the columns being orthogonal. But anyway, that's assuming C is square, then you get a unitary matrix here. Okay, so skip all the annoying part. So first annoying part is some lambda k equals 0. Second annoying part is C is not a square matrix, and let's ignore both of them. And finally, we get to the last part of this section is that yeah, so we can do this psi tilde as k tilde, and you can see we can apply the totally same logic to phi tilde because, well, their status are kind of equivalent, and so phi tilde is can be calculated from k tilde from some W matrix. Okay, and yeah, so psi tilde can be just calculated from phi tilde from this CW dagger matrix, and which will be a unitary matrix. Okay. So yeah, so that's a proof. It's quite an annoying proof, but then you get this quite nice result. Tells you that when the two ensembles are equivalent. Yeah. Nice to remember the result, but yeah. But a bit harder to find the application. We have about 10 minutes more, and I think then we can go to easier to prove but the actual important result. Okay, and big application of density matrix is this reduced density matrix. Okay, so I really want to talk about this. Okay, so reduced density matrix, what is this useful? Is you can say it's a part of our story on entanglement. So this is going to be a long story. Okay, so this is the first part. It's kind of a second part of our story on entanglement. So we start with entanglement. We say that we have some, usually it's, we only talk about bipartite entanglement here in this course. Okay. So we talk about entanglement as something happen to two quantum systems. We say we have system A, system B, and they can have an entangled quantum state between them. And we say entangled quantum state is some state that cannot be described by individual system. Okay. But the reduced density matrix is something funny. Is that it's saying, well, you have an entangled state, but I still want to see what I can do on my own system. Okay. So these don't describe everything, but the reduced density matrix will describe what if I only interact on my system, then what will I see and what can I get. Okay. So yeah, so reduced density matrix will be used to describe composite system, and usually it's entangled, and you want to see what one of the subsystems will see its quantum effect. Okay? And so let's start with the form generality. Let's assume our composite system is also in a mixed state, so it's in some density matrix rho AB. Okay? And now we define the reduced density matrix. And it's defined as this weird operation. So it's written as trace B rho AB. And so this trace B is known as partial trace over system B. And so it's really like the trace operator, but only work only on system B. And so end result is, so I guess, no, I didn't quite write here. Okay, so if we know rho AB is the matrix on HA tensor HB, then this rho A will become a matrix on only HA. Okay, and anyway, I should define the partial trace first. And here I have a bit of generating definition, I guess. So it's defined by two rules. So first is how we do trace on non-entangled state. Okay. So if you have your matrix being system A being A1K to A2 bra, and system B being B1K to B2 bra, then trace B is basically you only do trace on system B. So system A state is A1K to A1 bra, and on system B you become the trace B1 B2. So then you can use cyclic rule to calculate that this is just a number that's B2 inner power with B1, and then on system is A is A1 A2. Okay, so this is a definition of trace on this not entangled state. So some matrix on A tensor some matrix on B. Okay, and then you ask how we calculate this on other matrices. Okay, and how you calculate this on other matrices is you just extend this by linearity. So you have whatever matrix. If your matrix is some rho AB plus some sigma AB, then trace B over rho AB plus sigma AB is just trace B over rho AB plus trace B over sigma AB. Okay. And because every matrix, now we kind of go back to tensor product, because every matrix in this tensor space can be written as just element matrix element matrix in over this form. So you can have this A1, A2, B1, B2 being all computational basis. Then you can write every matrix with a linear combination of those computational basis matrices. Okay, so with those two rules, you can calculate the partial trace of every matrix. Okay, and I guess here we kind of do a bit of smuggling. So one thing you can check is that I guess not really in homework. So I guess homework question mark. So we smuggling a bit of thing here is you should check that one and the two are consistent. Okay, because yeah, consistent. Yeah, because we define one on many vectors. So here the A1, A2, B1, B2 can be everything. There can be A1 can be linear combination of other vectors, etc. And so you can check that actually 1 itself satisfies linearity, etc. So it's a homework question mark. If we find a space for homework, then maybe we'll ask you to do this. And if not, then you can also check yourself that this 1 satisfies linearity. Okay, for all the A1, A2, B1, B2. Okay, and anyway, let's say a little more about the rule. So as we say, our density matrix was on the system HAB equal to HA times HB. And then you do partial trace, then you back to a matrix on HA. And I guess it's better to see this in an example. And yeah, let's see our favorite integral state EPR pair. We have our beta 0, 0 equal to 1 over square to 0, 0 plus 1, 1. And we want to see what's the density matrix on A. And I guess here is the first time we do a complicated density matrix operation calculation, and you kind of see that people usually don't like calculating in density matrix because there are a lot of things to write down. You see that beta was 0, 0 plus 1, 1. Then first you write down its density matrix is this. Well, you need to expand this. So you need to have this and times is as joint. So there are 2 times 2 photons here. So 0, 0, 0, 0, and 0, 0, 1, 1, 1, 1, 0, 0, and 1, 1, 1, 1. Okay. Yeah, so usually if you can, people avoid writing density matrix, but sometimes you need to. Anyway, so back to calculating our trace B. We have photons, and by linearity, we do trace B on each one of them. Okay. I guess, oh sorry, I should not have trace B here. Okay, so we do trace B on each one of them. So we'll need trace B. So we trace B, and yeah, so basically we trace on the B part, and basically we have an inner product on the B part. So the first term we have A part being 0, 0, and the B part we have an inner product between 0, 0. Okay. And the second term we have A part being 0, 1, and then we trace on the B part is 1 cyclic to before 0, so we have inner part between 0, 1. Then this term we have 1, 1, 0, 0, so A part is 1, 0, and B part 0 cyclic before 1, and then lastly we have A part 1, 1, and B part being traced, so cyclic before here. Trace the B part and use cyclic property, it becomes 1 inner product with 1. Okay. And then you see that the inner product between 0 and 1 is 0, so this term disappears, this term disappears. And the end result is that you get also this inner product is 1, inner product is 1 here, so the end result is 1 half 0, 0 plus 1, 1, so you have 1 half times identity, so you get a totally mixed state. And yeah, so this is an interesting result to remember, that is whenever you have so when you have a Biot state, so here we only prove for EPR pair, but actually this is true for any Biot state. So you take the density matrix of a Biot state, so either A part or B part, it will become a totally mixed state. So kind of it doesn't, sometimes we like to think a totally mixed state doesn't contain information, but so it's just totally noise here. But I guess depend on your interpretation of information theory, also sometimes it means it makes more information. So depend on whether you think noise is information or not. Anyway, this is a totally mixed state. Okay. Yeah. Okay. And I guess here we also kind of see that let's talk a little bit about entanglement. So this is an integral state because the A part and the B part are both totally mixed state, and they can easily calculate that if you have a totally mixed state, tensor with totally mixed state, will be a totally mixed state on AB part and that doesn't equal to this entangled state here. So that's another way to check your state is entangled just with density matrix. But actually, let's digress a little bit. So for density matrix, there are actually different ways to define entanglement. Okay, so sometimes people will say, yeah. So this is the most basic way to define entanglement, but just know that there are actually several ways to say. Several ways for people to say entangled density matrix is entangled or not. Okay, and yeah, I guess we can write a little bit here. A bit of a side story is that sometimes people think about if you have a classical probability mixture of entangled state. Of not entangled state, and you kind of think it's also not entangled. Okay, so you have rho AI and tensor rho BI. Okay, so by our definition of entanglement, this can be still entangled, but people feel like you are only having classical mixture here instead of quantum superposition between your A part and B part. So this is what we call the separable state, and yeah, and sometimes it's still not entangled, yeah. But this is HR thing that will not be used in course, but yeah, it's something nice to know. Okay. Then if no question, we have 1 minute left, so I think we can stop here. And we'll continue with our density matrix next class, and yeah, maybe we'll also talk about purification, which will be reverse operation on this partial trace. Okay. Yeah, so see you next Tuesday.